plays soccer has no major impact on society by itself, it will definitely be a notable achievement, forming significant technological landmarks and foundations. This is the primary objective of the RoboCop Challenge, which outlines and specifies rules in the hopes that, by the middle of the 21st century, a team of fully autonomous humanoid robot soccer players shall win a soccer game, complying with the official rules of FIFA, against the winner of the most recent World Cup. However, the goal is ambitious and cannot be met at the present time. This project instead specifies a simpler, modified version of the RoboCop F180 small-sized league rules, in which the objective is simply to navigate a soccer field, acquiring the ball and kicking or dribbling it into the goal, while constantly avoiding obstacles.
The robot captures a 640 by 320 pixel image in BGR. This is then converted from BGR to HSV format in order to minimize the effects of lighting. Once in the HSV format, color-based thresholding is then applied to the image in order to extract the desired object from the image. The resulting image mask is then processed in order to close holes within sections and remove stray pixels. Information such as the object's centroid, length, and width are extracted from the final image mask. From this, the object's range can be determined through the analysis of the object's lowest point, as well as the bearing gained for the horizontal component of the object's centroid. This data is returned to the AI subsystem in meters and degrees for range and bearing respectively. Alternative approaches were taken due to the camera take as long as 3 seconds to capture and process the image. The resolution was lowered in half to 320 by 340 pixels. This decreased the time to 1.2 seconds, but reduced the image detail and compromised the thresholding and limited the vision system's ability to return accurate data. Instead, an alternative method was used using the camera's video port to capture images continuously. This reduced the processing time significantly to 0.245 seconds, while only suffering minor loss in image detail.
The approach taken for the design of the drive system was one of simplicity for a few reasons. Firstly, having a simple design allows for quick replacement or modification of parts and reduces the number of potential failure points. It also allows the robot to remain as cheap as possible. The design is an omnidirectional drive utilizing 3 custom 3D printed wheels, each equally spaced around the circumference of the robot. As with all OmniDrive systems, this allows the robot to translate in any direction while simultaneously rotating. This kind of motion is highly desirable for a robot capable of playing soccer. The wheels are powered by 155:1 micro metal gear motors with built-in encoders. The encoders relay information about the current velocity of each wheel, which is then used to adjust the power sent to the motors to maintain a specific heading angle and velocity using a PID controller. The motors allow the robot to consistently exceed the required design speed of 0.5 meters per second. The chassis is split into 3 main layers, each laser cut from a piece of clear acrylic. The heaviest components, such as the lithium-ion battery, are placed as low as possible to keep the center of gravity low on the robot, allowing for faster acceleration and deceleration without slipping or tipping over. The camera is on a pivoting mount that can be placed at one of 4 potential positions on the chassis, allowing flexibility of the perspective of the camera. A dribbler was also added to the robot to maintain possession of the ball while the robot is moving, but due to limited testing, the system did not function as required. All of the components are mounted within a 3D printed cover to conform to the F180 small size league specification.
Specifications of the AI and navigation require that the robot must be able to function autonomously, interpret sensory data, communicate with the vision system, navigate without collision, search for the ball and goal, and account for processing limitations. As such, many different navigation strategies were considered for the task, and due primarily to constraints, neither EKF SLAM nor potential fields were used, largely due to the lack of distinct landmarks, dynamic obstacles, as well as insufficient sensory data. In conjunction with the processing limitations of the Raspberry Pi, a more discrete, sequential approach was taken, which involved the robot taking a step of 0.1 meters before reassessing its situation based on the current state, and a decision tree, adjusting for bearing and executing an action. This would ensure that the Pi had sufficient time to process images and reach a decision before allowing the robot to execute its next action.